we've been talking about limits, but we've yet to really define what a limit is, right? So far, we've kind of been treating a limit as something, as x gets close to something, what does f of x do? So in this graph here, maybe we could call this function f of x, and then we have this point A, right? So um, down here is A on the x-axis, and we're going to let x approach A on the x-axis, and then we're going to wonder what does f of x approach. Well, it's going to approach some limit L. Okay, so there's our L, and we have f of x on our y-axis, technically approaching this limit as x goes into the point A, right? But all of that kind of feels a little wishy-washy, right? That doesn't feel super mathematical, saying, oh, x is getting close to something, right? And you can imagine, especially mathematicians, back when calculus was being developed, being very concerned about this getting close to business, right? Because mathematicians want a lot of rigor. They're doing very rigorous work, very precise work. And suddenly you have this whole branch of mathematics where the entire basis is talking about something getting close to something when you can't really say what that means. So back in the early 1800s, people were really beginning to question the validity of calculus in general. And though people had been using calculus, some of the mathematicians were beginning to wonder if it was valid at all, because it couldn't be put on any kind of rigorous mathematical footing or logical footing. And luckily, two mathematicians by the name of Cauchy and Weierstrass, in a sense, saved calculus by putting it on a rigorous logical footing with this idea of a limit. And that limit is known as the Epsilon-Delta definition of the limit, right? The Epsilon-Delta definition of a limit. Definition of limit, which we study now. So if nothing else, by doing these epsilon-delta proofs, we were giving a nod to history and the fact that calculus finally got put on a firm mathematical grounding, and we're not just having to talk about something getting close to something and waving our hands around and hoping for the best, right? What we'll develop right now is a very, very solid logical foundation on which the limit can rest, and we'll go from there. Now, try not to be too put off by this definition at first. It's not as bad as it looks, but it does look kind of scary the first few times you see it. But we'll develop a way for doing these proofs that's pretty straightforward, and we won't get too deep into the weeds with this. Of course, if you take an analysis class further, you'll do a whole bunch of these epsilon-delta proofs. You'll become a pro at this somewhere in your junior or senior level year of a math major. But for now, we're just going to get our feet wet with it and try a few proofs. So let's get a good conceptual idea of what this means. Epsilon-delta proofs. So what we're talking about specifically is the limit as x goes to a of f of x equals L. Okay, so that is the whole entity that we're focusing on here with this entire epsilon-delta business. And how it works is you essentially look at the limit L and say, okay, give me some range within L. You can give me any range you want. So here we go. There I've defined kind of a range around L. And that distance that we've gone off of L on the y-axis, we will call that epsilon. So let me clear out some of this stuff here. Okay, so we are within epsilon of L on the y-axis. And we essentially trace this back to our function and then down to the x-axis. And note that by doing that, we create a range down on the x-axis around A. We have this range down here, right? And as long as x is within this blue range of A, right, anywhere in here, so maybe I could pick some value right here. We go up here, we're going to be within this epsilon distance of the limit L. Okay, so we want to make that idea rigorous. I could pick anything down in this blue range. It's going to be go up to the function, and we'll still be in this epsilon of L on the y-axis. But to be extra safe, I'm going to take the smaller of these two distances. Note that one is very wide here, and one is very short. So I'm going to take the shortest distance here. I'm going to call this distance delta. This is the Greek letter lowercase delta. This other one is epsilon, the Greek letter, lowercase epsilon. It's actually kind of there's a couple different versions of the lowercase epsilon. So this is the one that looks like a backwards 3. So if I want to talk just about being within delta of A, that's going to be the safest bet. So we pick the shortest distance. So here I'm going to go off delta from either side. So what I can guarantee is as long as I pick a point within delta of A, trace it up and take the function value of it, then we're going to be within epsilon of our limit L. And what that's doing is giving us a rigorous definition of a limit. What I'm saying is you can give me an epsilon no matter how small you want, right? Give me any epsilon you want, no matter how small. I will find a delta that's so small that as long as I start within delta of A for my x value, I can guarantee that the f of x will be within epsilon of L. So basically, like, you give me epsilon, no matter how small you want, I'll find a delta even smaller that as long as I squeeze within this delta of A, I will be within your epsilon of L. I mean, it seems both trivial and confusing at the same time, but it's really profound what this did. Because now we have a way to rigorously talk about limits that we can put through mathematical testing and jargon and logic and all that. So let's take all of this that we've said and put it into words, and then we'll take those words and translate them into mathematical symbols, and we'll get something that looks really quite incredible, if not a little off-putting at first. Okay, so here it is. When we say that the limit as x goes to A of f of x equals L, this means that for any epsilon greater than 0, okay, so that's where I said you can give me any epsilon up here as long as it's greater than 0. So for any epsilon greater than 0, there is some corresponding delta greater than 0. So that's where I said I can give you a delta that's so small, right? I give you, it's usually very small, right? We'll just assume these things are small, such that as long as x is within A of delta, that's what this 0 less than the absolute value of x minus A less than delta means. The way we talk about distance from a point is by using this absolute value. So this business here, absolute value is the distance. Okay, distance. So we're saying as long as x is within a distance delta of A, and remember delta is very small, right? We're choosing delta so small that as long as that happens, then the absolute value of f of x minus L, which is also a distance, okay, so this is also distance, all right, of f of x from L, this is up on the y-axis now, will be less than whatever point epsilon we're looking at. So give me an epsilon, I find a delta such that this distance within delta on the x means that we are within epsilon up on the y. And again, just to draw this in visually, right, so we're picking some x here within delta of A. We follow it up to the function and back to the y-axis. And what this is saying is because we're within delta of A, we're guaranteed for our f of x to be within epsilon of L on the y-axis. And indeed it is. Now, this definition is written in logical terms, right? As soon as we start talking about for any epsilon, there is a corresponding something. And we have an if-then statement, right? So these are things, this is the logical footing that calculus needed. And even this is a little wordy, right? There are certain symbols that we use in logic, just like there are symbols that we use in mathematics, right? So in math, we don't write the word plus over and over again. We use the symbol, we use the plus symbol. So just like that, there are symbols that we use in logic that correspond to these words. So here's the same statement, the same, I guess, definition of a limit written with the standard logic notation. So here it is in all its glory, the Epsilon-Delta definition of a limit. And it says that the limit as x goes to A of f of x equals L means, and this is the same definition we have above, it's just written in the logic notation. So this upside down A is for all. So we have for all epsilon greater than 0. So for all is what that means. It's a really useful symbol. or we could say for every, but the A kind of means for all. Okay, for all epsilon greater than 0, backwards E means there exists. There exists. Right? Look how hard it is to write that, whereas I could just write a backwards E instead. There exists some E, or there exists some delta greater than 0. ST is such that, okay, such that, all right, I always love getting new mathematical notation. As long as, so we have the 0 less than x minus a less than delta. So why do we have this 0 in here? This tells us that x does not equal a, because we're letting x get close, arbitrarily close to a down on the x-axis, but we're not actually concerned with what happens at x equals a. So this keeps us from ever actually hitting a, so we don't have to worry about what happens at the point x equals a. Okay, so as long as this distance is less than delta, so this is an if-then statement. So this double right arrow is if then. Then. So what that tells us is this is our if part. If 0 is less than the absolute value of x minus a is less than delta, then this happens. Then the absolute value of f of x minus L is less than epsilon. So for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. And just like that, we have rescued calculus from the dust heap of history that it was destined towards if Cauchy and Weierstrass wouldn't have come up with this rigorous definition that saved the limit, allowed mathematicians to keep on working on this in a formal setting, and really restored the reputation of calculus as something that's worth studying and worth continuing. So if you really can't stand this version of the epsilon-delta limit definition with all these symbols, feel free to use this more word-centric definition up here. This is okay too, right? It all means the same thing. Let's try an example. Okay, here we're given a specific function. It's actually the same function we had drawn up before, but now I've labeled some exact points. And so we have x equals 6 is the point we're interested in here. Okay, and we're having an f of x, f of 6 equals 5. So our main values we're looking at is 5 on the y-axis and 6 on the x-axis. So now to the exercise itself. It says if epsilon equals 2, so epsilon is always the value on the y-axis, delta is always the value on the x-axis. So epsilon equals 2 is on the y-axis. It's always the function value that we're talking about when we're talking epsilons. So what it's saying here is if epsilon equals 2, so we're looking at all the stuff that is within an epsilon of 2, so epsilon equals 2, so within 2 of 5. So we're going to go up to 7 and down to 3. So it essentially defines this range here around the point y equals 5, or f of x equals 5. Okay, so you want to take this range and essentially kind of backtrack it back to the function and then trace it down to the x-axis. So delta is always on your x-axis. Epsilon's on the y-axis, delta's on the x-axis. Find some delta such that if x is within delta of 6, that's what this business here means, 0 less than the absolute value of x minus 6 less than delta. That means x within delta of 6, Okay, as long as x is within delta of 6, then f of x will be within epsilon of 5. That's what absolute value of f of x minus 5 less than epsilon means. F of x within epsilon of 5. So when we trace this whole range on the y-axis back to the function and down to the x-axis, we get a new range down on the x-axis between that goes from 3 to 7. And remember, our point of interest is 6 here. So we want to think of delta as a radius off of 6 here on the x-axis, right? So delta could go over to 7, so we could choose delta equals 1, or we could go all the way over here, maybe delta equals 3 to get us all the way to 3, or something in between. But notice if we chose delta equals 3, that would be fine to the left of 6 here on the left axis. But if we went out 3 to the right of 6 on the y-axis, we'd be out here at 9, and 9 is going to be well well outside of the range of this epsilon on the y-axis. So you essentially look at the distances in both directions and choose the smallest. So I'm going to look right here, and I'm going to let delta equal 1. So as long as I'm within 1 of 6 on the x-axis, yeah, we lose a little bit here on the left, but that's okay. We can always be smaller than delta, but we can't be bigger. So we want to choose delta really in close towards our x value of interest. So I'm just going to choose delta equals 1 because that gives me the smallest distance here that keeps us within epsilon. That's guaranteed to keep us within epsilon on the y. So that's essentially how we wrap up the problem. We just say, okay, let delta equal 1. Boom, as long as we're within 1 here on the x-axis, all right, we have a new point here. As long as we're within this range of 6, we are guaranteed to be within epsilon of f of x on the y-axis. So you essentially choose the smaller of the deltas, and that's how you wrap up these kinds of fine delta examples.